This is Chapter 3, Vectors in Physics. We'll be using vectors a lot this year. Now, if you've learned vectors in math, please just be patient and bear with the review. Review never hurts. But some of you may have only seen vectors very briefly before, or maybe you're just kind of rusty. So I think this is a good review of vectors for all of us.
First, let's distinguish again between scalars and vectors. So let's talk about distance. Distance is the length of the actual path taken by an object. So if we're talking about the distance from A to B, we have to think of the total path, the path which is curved and long. Well, that would be 20 meters. Okay, so that's a distance. The distance traveled in going from A to B. It's not a straight line distance. And also, we're not talking about the direction because really the direction kept changing anyway. All we care about is the total length of the pathway. So a scalar quantity contains magnitude only and consists of a number and a unit. So 20 meters, the distance in this particular example, is a scalar. 40 miles per hour is a scalar. 40 miles per hour, as you know, is a speed, but we would not call it a velocity because the direction is not specified. And 10 gallons, gallons would be a unit of volume. Well, volume has no direction. It doesn't matter. All that matters is the magnitude. So these are all scalars. Now, displacement is a vector quantity. Displacement is the straight line separation of 2 points in a specified direction. And so going back to the last screen's example, we still have points A and B, but now if we look at the straight line distance, well, we can see that B is 12 meters away from A at 20 degrees. And that is different. That is very different, as you can see, from the D, or distance, of 20 meters. For one thing, 12 meters is shorter because it's a straight line, but also since this is a displacement, we have to mention a direction, and that's 20 degrees. Now you might be wondering why S. Well, S is the standard symbol for displacement in physics, and so get used to using it now. You'll be seeing S a lot this year. Whenever you see S, it means displacement unless specified otherwise. If you want to help yourself remember it, just think of displacement. Displacement. Dis with an S. All right. Now, a vector quantity contains magnitude and direction, a number, unit, and angle. For example, 12 meters at 20 degrees. We have a number, 12. We have a unit, meters. And we have a direction, 20 degrees. Another example would be 8 kilometers per hour north. That's a velocity vector. It has a number, 8, which we call the magnitude, of course. It has a unit, kilometers per hour. That's a velocity unit. And it has a direction, an angle, north. North is just 90 degrees of east or 90 degrees of west. So it implies an angle. Symbols for vectors. Vectors are often written as a capital letter or a lowercase letter with an arrow over it. So for example, the vector v, v is often a symbol used for velocity vectors. It can be capital or lowercase with an arrow over it. And that arrow, of course, is the vector symbol. Now, magnitudes of vectors are written with single or double lines around the vector symbol, or simply as a letter. So we could have capital V with the arrow over it and two parallel lines around it. Or we could have little v and the arrow over it and those single vertical lines around it. Or we could just have v. And for simplicity's sake, most of the time in this course, when we're dealing with vectors, if you just see the letter, then that's referring to the magnitude of the vector. And if you see the letter with the arrow over it, then that's referring to the magnitude and direction of the vector, or simply referring to the vector when talked about in a sentence or in a problem. Okay, so for simplicity's sake, the just letter by itself, or the simple letter, will stand for magnitude in this course. Adding and subtracting vectors. All right, let's suppose that we have a vector displacement A, which is 5 paces to the north. We have a vector displacement, or displacement vector, east, 3 paces to the east, and that's the displacement vector B. We have the displacement vector C, which is 4 paces to the southeast. And we end up at the treasure. Now, I wanted to talk about this in order to introduce the concept of adding vectors. So when you add vectors together, you're not just adding magnitudes. You're adding magnitudes and taking directions into account to end up with a final or net vector that has a certain magnitude and direction based on all the different vectors that were part of the sum. So what you do is you place the tail of each vector at the head of the one before it. The sum points from the tail of the first to the head of the last. So the sum that we're talking about here is a vector sum. Okay, it's important for you to understand the distinction. A vector sum includes magnitude and direction. It's not just magnitude like the sums that you are used to. And another name for a net vector is a resultant vector. And resultant is going to be a much more common term when we're talking about a vector sum. Now going back to the idea of a vector sum. All right, so we have this displacement vector, 5 paces to the north, 3 paces to the east. Notice that no matter where we put these vectors, we're going to end up being in the same place. Okay, so this is going to be kind of a messy drawing, but it's just to illustrate what I mean. Let's suppose that we started at the sycamore tree, right? This origin is right at the center of the sycamore tree. And let's suppose that instead of 5 paces north, 3 paces east, and then 4 paces southeast, we did a different order. We did 4 paces southeast. Try my best to draw that now. 4 paces southeast. And then we did 3 paces east. Notice that I'm going 3 paces east. And then at the end we do 5 paces north. And notice how I end up in the same exact spot, even though my order was different. Okay, now let's try it again, and let's do it a little bit differently. Let's say that first we went, starting at the sycamore tree, first we went 3 paces east, 3 paces east, and then we went 5 paces north, and then we went 4 paces southeast. Notice how we're going to end up at the same exact place at the treasure. So my point is that when you're doing vector sums, the order of the addition doesn't matter. All that matters is that you place the tail of each vector at the head of the one before it. And then the vector sum points from the tail of the first to the head of the last. Okay, so with vector addition, you are taking into account both magnitude and direction. But no matter what order you do it in, you will end up with the same resultant or net vector. This method of vector addition is known as the tip-to-tail method. It's the most common method, and it helps us to visualize, with a sketch, what's going on with the vector additions. Now to add vectors v and u, so we have this red vector u here and a black vector v, And remember that vectors, it doesn't matter where they are in space. All that matters with a vector is its magnitude and direction. Okay, so going back to a little sketch, if I drew vector u here instead, notice that it's on a different part of the page, this vector u that I've drawn. However, it has the same magnitude and the same direction, then it's considered the same exact vector. Okay, it's still vector u. It does not matter where you draw a vector u. All that matters with vectors is the magnitude and direction of the vector. Doesn't matter where it's drawn. Okay, so to add vectors v and u, you place the initial point of u at the terminal point of v. You draw the vector with the same initial point as v and the same terminal point as u, and you'll end up with this. So this is the vector sum v plus u. Notice that we have we draw v, and then we put the tail of u on the tip of v, and then we end up with our resultant vector, or our net vector, that has its initial point at v, the same initial point as v, and the same terminal point as u. And that would be the vector sum v plus u. One more image about the sum of two vectors. So again, remember that with vectors it doesn't matter where you draw them. If we want to add u plus v, well, notice how this u here on the left is exactly the same as this u here on the right, same magnitude and direction. And this vector v here on the lower left is exactly the same as this vector v on the upper right, because it's the same magnitude and direction. And so we can draw vectors anywhere we want in order to visualize the vector sums. And so notice how clearly we can see that here, if you look on the right, we have vector u plus vector v, and that gives us a resultant u plus v. Example 1. Add these two displacement vectors and draw the vector sum, or the resultant. So we have a 10-meter displacement vector that is going right, or east if you want. We have a 15-meter displacement vector going down, or south. And so what I want you to do is draw the vector sum. Okay, so pause the video, do that on your own, and resume when you have your answer. Okay, you should have come up with this. You can draw the 10-meter vector anywhere and the 15-meter vector anywhere. We're going to line them up with the tip-to-tail method. And so we have the tip of the 10-meter vector lined up with the tail of the 15-meter vector. And then we can clearly see the resultant will look like this. It goes from the initial point of the 10-meter vector to the terminal point, or tip, of the 15-meter vector. Now, how did I know it was 18 meters at 56 degrees southeast? I didn't ask you to find the magnitude of the resultant vector, and I also didn't ask you to find the direction. My question to you is, how did I know that the magnitude of that resultant is 18 meters? And how did I know the direction of the resultant was 56 degrees southeast? Okay, so if you didn't figure that out already, then we have to review some trigonometry, and that's what we're going to do next. Trigonometry review. So this is our sample right triangle here on the upper left, and what I'm going to put on this screen are things that you really should have learned already before coming into the course, because if you look on your textbook cover, the title of the textbook, title of the book that we're using is Physics, Algebra, Trigonometry. In other words, our book presupposes knowledge of trigonometry. Our book isn't designed to teach trigonometry. And so this really should be review. If it's not, then then you need to talk to me about how to rectify that situation, because this course does heavily use trig, and so if this stuff isn't review for you, then talk to me at some point, and we'll have to figure out, you know, some kind of solution for you. Now, for most of you, this is review, but don't skip it, because it is important review. And also, the good thing about this review, if you know, you already know your trig, is at least you can know what part of trig we will be focusing on, because there is a lot to trigonometry, and we're not going to use all of it in this course. For example, we're not going to be using a lot of the unit circle stuff, or the trig identities, or even the law of cosines. But we will be using all the trig that we're going to see on this page. Okay, so the first thing, and this is the most obvious thing, right, from the Pythagorean theorem, the hypotenuse squared equals the adjacent side squared plus the opposite side squared. Or if you want to think of it this way, the hypotenuse squared equals one leg squared plus the other leg squared. All right, so we're going to write that as r squared equals x squared plus y squared. Now, a corollary of that we will use even more is r equals root x squared plus y squared. And this we'll be using a lot, because this is how we find the magnitude of a resultant. R equals square root x squared plus y squared. Now, another thing you should know already is that y over r equals sine theta. In other words, look at theta and you'll see that y is the opposite side. R is a hypotenuse. Opposite over hypotenuse is sine theta. Now, the corollary, which is more important, is that y equals r sine theta. We'll be using this a lot. Y equals r sine theta. And you can see algebraically why that's true, because if this is y over r, well, you just multiply both sides of the equation by r, and you end up with y equals r sine theta. X over r equals cosine theta. So x is the adjacent side. The adjacent over hypotenuse equals cosine. And the corollary, x equals r cosine theta. Y over x equals tan theta. So opposite over adjacent equals tangent. This is part of the definition, one of the trig function definitions that you've already learned. But the corollary is even more important than that, which is inverse tangent y over x equals theta. Inverse tangent y over x equals theta. Now, all inverse tangent means is the angle whose tangent is. In other words, that's another way to read this. That whole tan minus 1 y over x, that whole thing on the left side of the bottom right corollary can be read as the angle whose tangent is y over x. The angle whose tangent is y over x is theta. Now, on your calculators, you can find the inverse tangent button. Inverse tangent, by the way, is the same as arctangent, and so sometimes you'll see it symbolized arctan. But if you want to find the inverse tangent button on your calculator, and in this course, the standard calculator is the TI 83 plus and 84 plus family of calculators. All you do is, okay, first you find your tangent button, and notice that right above the tangent button you have the in different color you have the inverse tangent, or tan to the -1. It looks like tan to the -1. And so to do the inverse tangent, you just do second tan, because second tan will select the tan to the -1 function instead of the tan function. If you need calculator help, we can just do that in class. Finding components of vectors. If I travel in a northeast direction, it means that one component of my motion is north and the other component is east. All right, so we don't, this isn't really too foreign for us, the idea of components of vectors, because it's kind of a common sense notion. In fact, the word northeast kind of lends itself to this idea of components, because in the very word itself, you can see that there's a north component and an east component. A component is the effect of a vector along other directions. The x and y components of the vector r theta are illustrated below. All right, so here we have vector r, and it's at an angle theta. This vector r has a horizontal component of x and a vertical component of y. And the vector sum is r equals vector x plus vector y. So vector r equals vector x plus vector y. And notice that this goes back to the tip to tail method. We have x, and we lay that out. It's a horizontal vector. And then we put the tip of x lined up with the tail of y, which is a vertical vector. And notice where the tip of y ends up. It ends up right here, which is also going to be the tip of our resultant vector. So vector r is the vector sum of vector x and vector y. Now, very importantly, the corollaries, two of the corollaries from the previous slide, x equals r cosine theta and y equals r sine theta. We will use these equations in order to calculate the magnitude of x, vector x, and the magnitude of vector y. Example 2. A person walks 400 meters in a direction of 30.0 degrees northeast. How far is the displacement east and how far north? And if we want to fill out the sketch, we have our resultant labeled with a magnitude of 400 meters. We're trying to find the x component. We're trying to find the y component. All right, so based on what you learned on the previous slides, you should be able to figure this out. You're going to pause the video and try to get it on your own, and then resume when you have your answer or if you get stuck. Okay, so continuing with the answer, we can finish our sketch and put in the 30 degrees there. And we know that the x component, or the east component, is going to be the adjacent to that angle. And then we're going to calculate it with x equals r cosine theta. We also know that the y component, or northern component, is the opposite side, or the side opposite to theta. And we'll calculate it with y equals r sine theta. And you should have ended up with these answers. X is 346 meters east. Y is 200 meters north. Vectors and quadrants. So often when we talk about vectors, we will be talking about vectors in relation to the quadrants of the Cartesian coordinate system. Okay, so quick review on that. What I'm circling now with the mouse arrow is quadrant 1. What I'm circling now with the mouse arrow is quadrant 2. What I'm circling now with the mouse arrow is quadrant 3. And finally, what I'm circling now is quadrant 4. So it's 1, 2, 3, 4 counterclockwise from quadrant 1. Okay, so let's look at this vector. Okay, notice how with this vector in quadrant 1, you can see that the horizontal component is positive, goes right, so that's positive, and the vertical component is also positive. Now, let's look at a quadrant 4 vector. In quadrant 4, the horizontal component is positive, but the vertical component is negative. In quadrant 3, the horizontal component is negative, and the vertical component is negative. And finally, in quadrant 2, we have the horizontal component negative and we have the vertical component positive. Okay, so remember that vectors are often described as, or in relation to, the quadrants of the Cartesian coordinate system. Resultant of component vectors. Okay, so let's say we have this situation. We have vector r, which is the resultant, and its direction is angle theta. Vector x is the horizontal component, and vector y is the vertical component. To find the magnitude, it's r equals square root x squared plus y squared, one of those trig corollaries. And to find direction, it's theta equals inverse tangent y over x. Theta equals inverse tangent y over x. Example 3. A 30-pound southward force and a 40-pound eastward force act on a donkey at the same time. Find the magnitude and direction of the resultant force. Alright, so quick note. Force has direction just like displacement does. You can have an upward force, a downward force, an eastward force, a westward force, whatever. Okay, force has direction, just like displacement. So we can treat force vectors just as we have treated displacement vectors to find the resultant force. The procedure is the same. And as we'll see later, we can treat all vectors, velocity vectors, acceleration vectors, we can treat them all in the same way that we treat displacement vectors, because we can represent magnitude with length in that a longer vector has a greater magnitude and a shorter vector has a smaller magnitude. So you're going to draw a rough sketch. And don't worry, I'm just going to do the first part of the problem. Then I'll give you a chance to do it on your own. And this would be our rough sketch. We've got our donkey, and it doesn't like to be pulled. It's being stubborn. And it's being pulled with a 30-pound southward force and a 40-pound eastward force. So that's the rough sketch that you want to draw with, because that's all the information you're given. Okay, let's redraw in order to find magnitude and direction. So we have a downward force of 30 and a rightward force of 40. And then that's going to look like this. We have our resultant vector r. That's going to be the resultant force. We have vector rx, which means the x or horizontal component of the resultant. And we have our vector ry, which is the y or vertical component of the resultant. We've labeled the magnitudes that we know, and we are labeling the angles. So angle theta is this big angle that goes counterclockwise from the first quadrant. But the angle that we're interested in, or the reference angle, if you like, is the angle phi. The angle phi is really the only angle that we care about. Okay, so at this point, you should be able to figure out the magnitude of the resultant and the direction of the resultant based on what you're given. Pause the video, do that on your own, and then resume when you have your answer. Okay, so the magnitude, r equals square root x squared plus y squared. You should have come up with this. That would be a magnitude of 50 pounds for the resultant. And phi equals inverse tangent 30 over 40. And that is an angle of 37 degrees southeast. Remember, if you did this on your calculator and didn't get that angle, you need to check and make sure that you are in degrees rather than radians. Example 4. Find the components of the 240 Newton force exerted by the boy on the girl if his arm makes an angle of 28.0 degrees with the ground. Okay, so we can look at his arm, and that force he's exerting as the resultant force vector. And we can redraw to incorporate our givens. And so notice that we have our Fy here, or our vertical component. It's completely interchangeable. You can draw the vertical component over here, or you can draw it over here. I actually think it's much more helpful to draw it over here on the left, because then you can visualize the right triangle much more easily. Okay, so we've labeled our angle 28.0 degrees, and we know that the magnitude of the resultant is 240 newtons. Okay, so pause the video, find these components on your own, and resume when you have your answer. Okay, so the horizontal component, or f sub x, the x component, is, again, r cosine theta. And so we have 240 newtons times cosine 28.0 degrees, and that's 212 newtons left to the left. And our Fy, or our y component, our vertical component of the resultant, is r sine theta, or 240 newtons times sine 28.0 degrees equals 113 newtons up. Example 5. Find the resultant force acting along the handle of a lawnmower if its horizontal component is 254 newtons left and its vertical component is 159 newtons down. Okay, so again, helping you with the sketch. Remember, in the future, you'll be doing sketches on your own, but this is just to kind of get you warmed up. So we're talking about this, the lawnmower handle, right? And the force is acting right along the handle. It's a diagonal force at an angle theta that we need to find. And redrawing to incorporate our givens, we know that our horizontal component is 254 newtons left. We know that our vertical component is 159 newtons down. And we're asked to find our yellow F here, that is the resultant force, and the direction, or theta, of that resultant force. Pause the video, do those on your own, and resume when you have your answer. Okay, so you should have come up with this. F equals square root 254 squared plus 159 squared, and that's 300 newtons. And theta equals inverse tangent 159 over 254, and that is 32.0 degrees. Remember that the answers have to be with the correct number of significant digits, and that's why we're using 3 significant digits, since both of our givens have 3 significant digits. Adding and subtracting vectors. So adding vectors using components. This will be the most common way that we add vectors in this class. And you'll see that it's much easier even than the graphical method. It's based on the graphical method, but once you learn it, you can really just use the component method every time. So here's how it works. First, you find the components of each vector to be added. Then you add the x and y components separately, and you find the resultant vector. Okay, so it turns out that when you add x components of any number of vectors, you'll get the total x component of the resultant. And when you add y components of any number of vectors, you'll get the total y component of the resultant. Let's see how that works. Looking at this example, we're going to be adding vectors using components. And so we have 2 vectors here, a and b. C, the vector C, is the resultant, as you can see. No pun intended. It's the resultant, as you can see, of vector A and vector B. When you add vector A and vector B together, you get the resultant, vector C. Now, the problem is that even if you know the magnitude of vector A is 5 meters, and the magnitude of vector B is 4 meters, and even though you know their directions, it's really not so intuitive to figure out from that the magnitude and direction of the resultant. And so that's where the component method becomes very handy. So this equation here, c sub x equals a sub x plus b sub x, simply means that the magnitude of the horizontal component of the resultant vector c equals the magnitude of the horizontal component of vector A plus the magnitude of the horizontal component of vector B. And we can also say that c sub y equals the magnitude of the vertical component of vector A plus the magnitude of the vertical component of vector B. And this actually makes sense. I'm going to kind of draw this and so you can get a better visual representation of why it's true. But the nice thing for us is that if we have our horizontal components and we have our vertical components, we can just put them together and figure out the total horizontal and total vertical components of the resultant. Okay, so let's take a look at it. Let's look at this first equation here, which is c sub x equals a sub x plus b sub x. All right, so this black vector that I just drew here at the bottom, which begins at point O, that black vector represents the horizontal component of vector A. So this black vector here represents a sub x. Now, this black vector up here represents b sub x. Now notice how a sub x plus b sub x equals c sub x with this next move, because I can drop that vector down, and when I drop it down, look how they line up, and we see clearly that a sub x plus b sub x equals c sub x. And you can see how the horizontal component of this purple vector c, that magnitude of the horizontal component exactly lines up with a sub x plus b sub x. Now let's do a similar thing with a sub y plus b sub y. Okay, so this black vector here is b sub y, the vertical component of the vector b. And this black vector here is a sub y, the vertical component of the vector a. Now watch how they line up when we do this move here. And you can see clearly that a sub y plus b sub y equals c sub y. Okay, and now look at this purple vector c, which is the resultant. Notice how it has a horizontal component, c sub x, and it has a vertical component, c sub y. And of course, from those, we'll be able to get the magnitude and direction of the resultant. But it's really neat when you stop to think about it, how you can get the components of the resultant just by getting the components of the vectors that are added in order to make that resultant. Okay, so let's continue with the problem, and what we're going to do now is we're going to try to figure out the exact magnitude of vector c and the direction, or theta, for vector c. All right, now at this point, those of you whose trig skills are good enough will be able to figure out the magnitude and direction of c by using the component addition method I just showed you. And then once you get the components of c, you'll be able to get the magnitude and direction of c. All right, so those who are already familiar with trig should pause the video, find the magnitude and direction of c, and then resume when you have your answer. And those who are shaky on trig should just carefully watch the remaining steps. Okay, so a sub x equals 5 meters times the cosine of 60 degrees. And we know that, of course, because on the last screen we already saw as a given that the magnitude of a is 5 meters. And so r cosine theta, remember that the x component or horizontal component is r cosine theta? Well, that's where I get this from. R cosine theta is 5 meters times cosine 60 degrees. And that equals 2.50 meters. And I've drawn the 2.50 meters right here. So you can see that that is a sub x. Now a sub y is 5 meters times the sine of 60 degrees, because it's r sine theta. And that's 4.33 meters, which I've drawn here. 4.33 meters, and you can see how that is the vertical component of the vector a. Now b sub x, horizontal component of the vector b, is r cosine theta. And so we have 4.0 meters cosine 20 degrees, and that's 3.76 meters. And we see it here as that black vector, 3.76 meters. And finally, b sub y, or the vertical component of b, is 4 meters times sine 20.0 degrees, and we have 1.37 meters, which is illustrated here. So notice now that we have the horizontal and vertical components of both vectors A and B labeled with their magnitudes. And now, from the notes on the previous screen, you should be able to now give me the components of vector C by simply adding AX to BX and adding AY to BY. Okay, and this is what you're going to get. CX equals AX plus BX, which is 2.50 meters plus 3.76 meters equals 6.26 meters. And we have that vector, C sub x, 6.26 meters. And C sub y equals A sub y plus B sub y. And so 4.33 meters plus 1.37 meters equals 5.70 meters. And we have C sub y labeled there. And now we can see that since we have the horizontal and vertical components of the resultant, we can get the magnitude and direction of that resultant. So the final steps are to get the magnitude of vector C, square root cx squared plus cy squared equals square root of 6.26 squared plus 5.70 squared, and that is 8.47 meters. And we now label it here where I'm circling with the mouse arrow on the purple vector. 8.47 meters is the magnitude of C. And finally, to find theta, we do inverse tangent C sub y over C sub x, since C sub y is the opposite and C sub x is the adjacent. And that's 5.70 meters over 6.26 meters. And we're left with 42.3 degrees. And I've labeled it now on the graph, 42.3 degrees. Okay, so by using component addition, we were able to come up with first the components of the resultant, and then finally the magnitude and direction of the resultant.
Here's the classwork. Please write these numbers down. They will be given as a worksheet. See you in class.